Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So within this module, we are trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? So within the second module, we are currently on the fourth topic, that is process system call API. So, as the name of the topic suggests, in this topic, we are looking at the system call interface. To be specific, we are looking at the system call API of the Unix operating system and studying the set of system calls which are used for process management. Basically, we want to understand the system calls which allow us to perform operations on the processes. So, currently, we are discussing the system calls which help us to create new processes. And in the previous few videos, we have talked about the fork system call. So we have looked at the fork system call and understood that it is used to create a new process. So now we will study a similar system call that is used for process creation, that is the exec system call in the Unix OS. So the exec system call is used to run a new program. So let us see how this works and how it is different from the fork system call. Without further ado, let's get started. So before we start talking about the exec system call, let us recall how the fork system call works, right? Studying the fork system call will help us to understand why we need the exec system call. So this is a simple example that I have taken. And as you can see, this is a process, right? So as this process is executing, within the code of this process, there is an invocation to the fork system call, right? And when this fork system call is made, like any other system call, the control will be transferred to an appropriate routine, in this case, the fork routine inside the code of the operating system. So this is how we make the fork system call. And as we know, the fork system call works by creating a copy of the original process. So in this case, this process A is the original process or the calling process. And when it invokes the fork system call, we have a new process. The operating system, basically the fork system call, creates a new process by duplicating the original one, by making a clone or a copy of the original one. So here, although we have a new process, the program that is being executed remains the same. This new process is executing the same piece of code. It has the same instructions, the same values of the data, the same files which had been opened by the original process, the same values of the registers. Everything remains the same except for a few minor values like the process ID and so on, right? So the fundamental idea behind the fork system call is that although a new process will be created, but it will be executing the same program. And if you carefully observe this, then what happens is that if we only have the fork system call in the operating system, and if we only keep invoking the fork system call, then what we will have is we'll have multiple processes running the same copy of the program, right? We'll have several different processes, but all of them will be running the same copy of the same program, right? So this is where basically this is where the fork system call is not sufficient to basically, although it creates a new process, but it does not help us to execute new programs. So this is where the fork system call alone is not sufficient. That is why the in the case of the Unix operating system, we have another system call, that is the exec system call. This is basically, it complements the fork system call. It does not create a new process, but it allows us to execute a new program, right? So if you compare this with the fork system call, the fork system call creates a new process, but it executes the same program, whereas the exec system call does not create a new process, but allows us to execute a new program, a new binary, right? So in Unix operating system, the fork and the exec system call work are basically used together in order to launch new processes and new programs, right? So this is where the exec system call is helpful. So having studied why we need the exec system call, let us now see how does it work. So here basically I have a screenshot of the Linux manual page, and as you can see, this is a description of the exec system call. And the exec system call, basically the C library provides different variants of the exec system call. So although there is only one system call that is known as exec, the C library has different wrappers, so you can say different ways to invoke the system calls. And the difference in all these variants that you can see here, we have 6 different variants of the exec system call, lies in the way in which we supply the arguments to the exec system call. There are different ways, different options that are provided to the user in order to supply the arguments to the exec system call. That is why we have like 6 different varieties of the same exec system call. So this is like a family of library calls or library wrappers over the exec system call. So in this video, we are going to discuss one particular variant of the exec system call, that is the exec BP, right? So this is how the signature of the exec BP looks like. So first of all, let's discuss what does it do. It basically executes a new program, and the way you specify the program is by the name of the file. So in this case, as you can see, this is the first argument specifies the name of the file that has to be executed. Obviously, in this case, we are talking about a binary file. It's not a normal file. It's a program. It's a binary file that is executable. As we know that a program is a binary file that is a bundle of executable instructions and the data. So in order to invoke this exec BP variant of the exec system call, you have to specify the name of the binary file or the name of the executable. Apart from the name of the file, the second argument that we have to provide is a list of basically arguments that will be supplied to the new program that we wish to launch, right? So whichever program that we want to launch, whichever program that we want to be executed, it will start with a set of arguments, right, that we have to supply via this second argument to the exec VP system call. And this was about the arguments. And what does it return? Basically, if the exec VP system call or exec system call is successful, it does not return, right? It As you will see, once the exec call is successful, we start executing a new program. The old program where the invocation of the exec system call was there, that we never return to that program. We'll see how it works. So the return value of the exec system call is like this. If it is successful, there will be no return. If it is not successful, if for some reason the exec system call fails, then we return a value of -1 to the calling process, right? So this was a brief description of the function signature. We are going to study, as I said, one particular variant of the exec system call, which is exec VP. The other variants are also very similar. They just differ in the way we supply these two arguments, right? So first of all, let us understand these two arguments in more detail, because this declaration, that is const char star and char star const, can be confusing. So first of all, before seeing the examples of exec VP invocation, we are going to first of all understand the difference between these two expressions. So this slide basically explains the difference and helps us understand what is the type of each argument. So basically, the first argument is the name of the file. This is a pointer to a const char, right? As you can see, this is the description that I have written. The file is a pointer to a const char, whereas this argv, right, this is an array, right, of what? It is an array of constant pointers to char. So argv is an array of constant pointers to char, right? So first of all, how do you read these declarations? So there is a rule based way to read these C style declarations of variable names. I have attached a link to the like article where you can study how you can read this complex C declarations. You can go to that website and read further, but we'll not go deeper into that. But yeah, you don't need to. The point that I want to convey is that these declarations, you do not need to like by heart or mug up. There is a proper logical way to understand how do you read these declarations, right? So now, having understood what does these declarations mean, let us understand what exactly are they. So for that, I have a simple example from the Unix shell. So let's go over the commands that I have like given to the shell. First of all, in a particular directory, I have entered the ls command, so which basically lists the contents of that folder. So as you can see, we have a single file, that is foo.c, in this particular directory, right? And then I enter a command called which is the copy command. So the copy command takes in two arguments. The first is the path of the source file, that is the foo.c within the current directory, and the destination is the path of the second argument, right? The second argument is the destination path. So here the destination path is again in the same directory, and the file that we want, the new copy file that we want to be created, will be called bar.c. So this command is basically saying copy the contents of the file foo.c, which is in the current directory, to a new file in the same directory, and the name of the new file will be bar.c. And after this command, copy command has been executed, I have listed out the contents of this directory once again. So you can see we have a bar.c file, and obviously the contents of this file will be the same as foo.c. So why am I talking about this Unix shell and this command? So basically, if you see carefully, when you enter any command on the Unix shell, you are executing a new program, right? So all of these commands, that is ls, cp, there are many more commands that you supply on the Unix shell. All of these commands are actually program binaries. All of them in itself, they are some program, they provide some kind of functionality, right? So for example, the ls is a program which helps us to list out the contents of the current working directory, right? And the copy command helps us to copy one file to another file. So all of these commands that we provide to the Unix shell, all of these are programs. And what we specify when we are writing a command is the name of the program file, the name of the binary executable, and we also supply a list of arguments. So basically, internally in the backend, the shell uses the exec system call, right? It uses the exec system call to launch a new program, right? So if you see this command, then it has two parts. The first is the command name or the file name that we want to execute. And then we have a list of arguments. It has two arguments, that is the path of the source file and the path of the destination file. So now that you know that these commands are executed internally by the shell by calling the exec system call. And what does the exec system call expect? It expects the name of the file and the list of the arguments. And we also studied that the way these arguments are specified, that the file name is a pointer to a constant character, and the list of arguments, the argv, is an array of constant pointers to char. So let us see how are these two different, how do they look like, right? So this will give you a clear understanding of these variables. So this is how the file variable looks like. This is a pointer. As you can see, it is storing an address. So let's just assume that at address 100 we have a character, and this character is a const character. So this is basically a C style string. As you can see, this is a character array, a C style string, and it stores the name of the file, the name of the command, which is the cp command. So internally, when the shell executes the exec system call, it will specify the file name using something like this, right? There will be the file variable will be a pointer, and this pointer will be pointing to a constant character. So the red color signifies that we cannot change the contents of the character here. Although we can change the value of the pointer, we cannot change the value that it is pointing to. So this is the first part. Okay. Coming to the second part, argv is an array of constant pointers. So as you can see, this argv is an array. It has two locations, index 0 and index 1, and each location is basically a pointer. So when we say a pointer, it will be storing some address. So the first location is storing the address, let's say 200, and the second location is storing the address 300. Hypothetical example. Okay. And these addresses are pointing to a character, and basically again we have a character array, and these are arguments. The first pointer is pointing to the first argument, which is the path of the source file. You can see the foo.c. Also, both of these character arrays are terminated by a null character, right? That is how strings in the C language work. And finally, the second location is storing a pointer to the second argument, that is bar.c. So this is the name of the file, and this is an array of arguments. Now, if you see the difference, in the first case, the address is not a constant, right? The pointer is not a constant value. You can change this value. Whereas the location to which this pointer is pointing to, this is a constant character. You cannot change the contents of this array. So the rationale behind this is that you do not want to change the name of the file. Once the name of the file has been specified to the exec system call, it is a constant thing. We do not want to change the name of the file that is that the user wants to be executed. Whereas if you look at the arguments basically have constant pointers, but the location to which they are pointing to, these can be modified. Here the contents of the actual location cannot be modified, but the address can be modified. Whereas in this case, the address cannot be modified. Basically anything in the red color that I have specified cannot be modified. Whereas the location to which this address is pointing to, that can be changed. Okay. Again, the rationale behind this is that the operating system might want to modify the arguments before supplying to the new program. For example, this source path, if you see, it is a relative path. Maybe the operating system wants to uh, the way the operating system can be designed in this way, that the relative path might need to be converted to a full path, like absolute path. So in that case, we can modify the arguments as per the convenience of the operating system, right? So here the arguments can be modified, but this address cannot be modified. That is why it is a constant pointer. Whereas here, the name of the file, the actual contents of this character array, that cannot be modified. That is why it has been declared as a const character. So I hope this basically gives you an idea of what is the difference between pointer to const char and constant pointer to char. So this is what I wanted to explain in this video, right? In this slide. So now we have an understanding of this function signature, right? This is the exec system call. It basically is used to create and launch a new program, and we specify the name of the file that the name of the program file that we want to execute as the first argument. It is a pointer to a const character, right? It is a character array, and it cannot be modified. The file name cannot be modified. And the second argument we supply is an array of constant pointers to char, right? So the arguments can be modified by the operating system. So this was about the function signature. Now we'll see how actually the exec system call works. So now we'll finally understand how does the exec system call work. So let us again start with an example. Here you can see we have a process, and this is the code of the process, where somewhere we have the invocation to the exec system call, right? So let's start executing this piece of code. And when it hits this exec system call, the control will be transferred to the exec routine inside the operating system call. The operating system. This is how a system call works. The control is immediately transferred to an appropriate routine inside the code of the operating system. And as we discussed, the two arguments that are specified to the exec system call is the name of the file and the list of arguments. So just a clarification here. So here in this diagram, I have written exec, but in this video, we are discussing a particular variant of the exec system call, which is exec BP. Only the exec BP accepts the arguments in this format. The other variants of the exec system call have different ways of accepting the arguments, but nonetheless, I'll use the exec name only. But I mean, for this video, in the context of this video, you have to understand that these arguments are only for exec BP, the name of the file and the list of the arguments that have to be supplied to the new program, right? So after this is done, what the exec system call what this routine will do, it will take the name of the file and it will search on the disk, basically the persistent memory. It will search on the disk within the current directory whether this file is present or not, right? And if when it locates the file, it will load the program. So this is the binary file, this is the program, and it consists of the executable instructions and the data, right? It will load this program and replace the code and data of this process A with that of the contents of this binary file, right? So as you can see, the exec system call replaces the current program with a different one, with the new one, right? The name of the file we have specified, the name of the binary file or the program that we want to execute, we have specified. The exec routine searches for that file within the current directory. If it is not found in the current directory, it will also search in some other pre-configured directories as well. For example, in the environment variables that we have, there are certain paths that are defined, that whenever the operating system will search for a file, it will also search in those set of files, in those set of directories, right? So apart from searching in the current directory, the operating system will also search in the set of pre-configured directories which are part of the environment variable, right? And once it finds that file, that is a binary file, that is a program, it has the instructions and the data. What the exec routine does is that it reads these files, it reads the sections in this file and uses these contents to replace the current program that is being executed. So as you can see, no new process was created. In case of the fork system call, we duplicate the original process and create a new process. Here, we do not have a new process. It's the same process A, right? What we have done is that we have just replaced the program that is being executed by replacing the code and data of the current process using the contents of the file that was provided in the exec system call invocation. The next point is that the new program starts execution from main with the arguments that have been supplied. So as you can see, when we invoke the exec system call, we also supplied a list of arguments. So when the exec system call routine returns, right, when it returns, it will start execution from the main, right? It will not basically, if you see here, we are invoking the exec, it will not start execution from this point because this entire program has been totally replaced, right? And we have a new program in its place. So we'll start the execution from the first statement of main, and it will also take the list of arguments that was supplied, right? So when we invoke the exec system call, we supplied a list of arguments, so those will be passed to this new program, right? And this new program will start execution from the main using these arguments. So let me quickly recall what happened. So we were basically here, we invoke the exec system call, right, with these arguments, the name of the file and the list of arguments. Then the exec routine searches for this file on the disk in the current directory and some other directories also which are pre-configured. Once it locates the file, then it uses the contents of the file, it reads the code section, the data section, and replaces this program with a new one with the contents of this binary file. And now that previous program is replaced with a new one, right? And no new process has been created, it's the same process, it's just we are executing a new program, right? Remember the distinction between a program and a process. A program is just a binary file which consists of the instructions, executable instructions, and the data, whereas a process is a program in execution. So in this case, we did not create a new process, right? We only replace the program, we only replace the code section, the data section, and as we'll see some other the entire process address space is actually modified, right? So the same process is there, right, but we have a new program. And this new program, so once the exec system call returns, this new program will start execution from the main, and it will also take the arguments that were supplied as part of invoking the exec system call. So this was a basic description. So now let us see how does the exec system call exactly transform the process. We have said that we are not launching any new process, we are executing a new program by transforming the existing process. So let us take a look at it in more detail, that how does the exec system call transform the existing process. So as we discussed a few slides back, that the exec system call does not create a new process. It just transforms the existing one by replacing the program that is being executed, right? So as you can see, after the exec system call, this is the same process that is executing. It's just that the program that was being executed, that has been replaced with a new one, right? And that new program will be fetched from this file argument that you specify, which is a binary file on the disk, an executable file residing on the disk. So this is the new program that is used to replace the existing program, right, in the current process, in the calling process. So now we'll see how does this how does this all work out? How do we replace the contents? How do we replace the current program? We'll see that in more detail, right? So basically for that, understanding that, let's see this diagram. Here we have a process, and as we know, to represent any process, the operating system has a data structure which we know as process control block. So the process control block, as we have already discussed, it's a data structure which contains all of the information that is necessary to describe a process. So all the fields, all the pieces of information that are part of this data structure, they are in some way necessary to describe this process. And the operating system has a process control block to describe every process in the computer system. So there will be as many process control blocks as there are processes in the computer system. And associated with each process, it's a very important thing, a process address space. So the process address space basically consists of all the code and data organized in a proper way in different sections for this for this process. So with each process, we have a process address space. We have discussed these concepts in previous videos, right? So now when a process is executing, we'll now see how does fork behave versus how does the exec system call behave. So when the fork system call is executed, as we know, the original process or the calling process, we create a copy or we duplicate the calling process, and this is how it looks like. So basically, let's say that process A invokes the fork system call. So what the fork system call will do, it will create a copy of this, and this is the new process that is created. So process B is a different process, right? It's not the same as process B. I mean, talking in terms of, let's say, process ID, process A and process B are two distinct processes in the computer system, but the contents of this process control block, the process address space, basically all of them will be a copy of the original process. So the contents of the new process, right, it's a copy of the original process. It's basically the whole new process has been created by duplicating the original one. So now if you see, when this is same, the code is same, data is same, all the sections, the stack and heap, the process control block, everything is same except for a few minor things like the process id, all those minor details. Except for them, everything is the same. So the fork system call, although creates a new distinct process, it's executing the same program, it's executing the same functionality or the same piece of code. We can say if we only have the fork system call in the computer system, then all we'll have is multiple copies of the same program running, which will not be of any use, right? Now let's see how does the exec system call behave as compared to this. So now we have the exec system call, right? And let's say this is the process that we are starting with. So as we have discussed, the exec system call does not create a new process. No new process will be created like we created in the fork. We have this original process, and this is the process that we will work with. The exec does not create a new process. It transforms the existing one. This is the process which we will transform. How will be transformed? We will use the file that has been specified in the exec system call, right? This is the file. This is the program or the binary file, executable file that is residing on the disk. It has the code, it has the executable code, the data, right? All of this is bundled into a file. This is the new program that we want to execute. So the program that was being executed till now is a different one from the one that we want to execute. So after the exec system call is made, let's see how does the exec call transform this process. So the first thing that is done is that it will read the code and the data from the executable and override the current sections. So this was how the process address space looks before we invoke the exec call. It has some different code, some different data, and when the exec call is made, then all of this will be replaced by the instructions and data from the new program, right? The new program is basically we have compiled and we have a executable file. It has a different code, it has different data. All of that will be used to replace the code and data sections of the existing process. Next, the stack is reinitialized with the arguments that were passed to the exec call. So if you see here, along with the file name, we are also passing the list of arguments. And now that we want a new program to start execution, it will start a fresh execution. All of the contents of the stack, let's say there were some stack frames, some pending function calls from the previous program, all of that will be discarded. A new fresh stack will be created, and the list of arguments, right, that we passed to the exec call, those arguments will be used to reinitialize the stack so that the new program will start from a fresh point. It will start the execution from the starting of the main function with the new arguments, right? So this is how the stack section is modified. Then the heap and all the other parts of memory are also reinitialized, right? Basically the heap might have some allocated objects from the previous program, so all of them are kind of invalid. We are going to start execution from a fresh point, a fresh program. So all of the regions of the memory are reinitialized, right? The code and data is replaced, the stack is initialized with new arguments, the heap, all of the objects will be discarded, and we will have a fresh heap. So this is how the entire memory image of the old process is replaced with that of a new program, right? So this is how the memory looks like. The process address space defines how the memory looks like to a process. It has the code and data organized in different sections. And now that we have modified all the sections so that we are ready to start executing a new program, everything that was part of the previous program has now been discarded. So basically this is how it looked like, the process address space looked like before we made the invocation to the exec call. And after we invoke the exec call, all of those sections have been modified. So as you can see, this is how the exec system call uh, transforms the existing process. It has not created any new process. You can see we still have a process A, the same process control block is there. All we have done is that instead of creating a new process, we have just transformed the existing process, and most of the modifications that we have done are in the process address space. We have basically replaced the memory image of the previous program, and now what we have is the basically the new program. We have set the process address space so that we can start execution from the new program. So this is how the exec system call transforms the existing process. So now we will talk about the value that is returned by the exec system call, right? So we'll talk about both the cases, that is when the exec call is successful and the other case when it is not, right? So as you can see, let's start with the success case. Exec call does not return whenever it is successful, and it is like as if the calling program never ran. So what does this mean? So let's take an example to understand this. Let's say we have a process A and it invokes the exec system call. When it does that, the control is transferred to the exec routine inside the operating system. And as we can see, the arguments have also been passed. That is the name of the file and the list of arguments that is needed for the new program, right? So now what does the routine do? So the exec routine will find the program or the binary file that is specified by this file name. And then what it will do, it will load this, basically it will use this program to replace the program that is currently being executed in process A. So currently some different program is being executed, let's say, which is signified by this blue color. It is now replaced by a different program, and the new program I have specified by the gray color. So now basically there is no place to return. Now the execution starts from the main function in this new program. This exec call will not return to this point. After the statement after the exec call will not be executed, because this whole program has been replaced. There is no place to return to, right? If you see, this exec call is in the previous program, and after the exec call has been made, after it is successful, this whole program has actually been replaced, right, with a new program. In the new program, the execution will start from the main function, the first statement of the main function. So that is why when the exec call is successful, it does not return, right? So this is the case when the exec call is successful. Whenever we make an exec call and it is successful, the entire program, the entire code of the original process is replaced with the new program, so that there is no place to return to in the previous program, right? Now we are executing a new program, so the exec call does not return. And obviously in the new program, the execution will start from the first statement of the main function. The next point is that when there is an error, in that case, the exec call will return an integer value of -1. So let's take another example. Let's say this process A invokes the exec system call, and let's say it passes the arguments, that is the file name and the list of arguments for the new program. And let's just assume that this file name is wrong. It does not exist. In that case, the exec call will not be able to find any binary file on the disk. It will not be able to locate that program. I'm just giving one of the examples why this call can fail. And when this call fails, then it will definitely return to the calling program, and the value that is returned is -1. So as you can see, whenever it is successful, this whole image, this program will be replaced by a new one. So in that case, the code where exec call has been defined, it is replaced, so there is no place to return to. That new program will start execution from the main function, right? That was the case when the exec call is successful. Whereas if the exec call is it fails, then in that case we still have the same program, right? We do not replace the existing program. We are still executing in the same program, and when the exec routine returns, it will return to the statement that follows the exec call with a integer value that signifies the error, right? So this is how the exec call works. This is how the return value looks like in the case of exec system call. So now we'll see some real examples of the exec system call. We'll see some code and understand it in more detail. So let's see the first example. The first example that we have here, as you can see, it's a very simple piece of code written in C. This is the exec VP system call. And what are we passing here? Let's understand this. So first of all, there is a this args is an array of pointer to characters, right? So as you can see, we have character strings within this array, and here you can see it is a copy command. We will basically try to run the copy program via this piece of code. A few slides back, we basically use the copy command to copy the contents of a file named foo.c into another file called bar.c, right? A few slides back I talked about that command. So now instead of like typing those commands in the shell, we are going to see how we can execute that command programmatically. Basically, we are trying to execute the copy program, the CP program, from a piece of code that we are writing, right? So this is how similarly the shell will be doing it internally. It will be calling the exec call. So that is what we want to see. We want to see how any Unix command we can run programmatically without using the shell, without typing it directly into the command line. We will use those commands and pass it to the exec system call. So in this case, I am using the exec VP version, as you know, and this basically this array contains the arguments that we will be passing to the exec VP system call. So the first argument, as we know, will be the file name, and arg0 is basically CP. CP is the file name. CP is the name of the binary that we want to execute. And then we pass the full list of arguments. So let us see the convention that is followed. So these are the rules that you have to follow. Argv, that is the second argument. That is the list of arguments that we need to supply to exec VP, is an array of pointers to strings. In this case, character arrays is an array of pointers to strings passed to the new program as command line arguments, right? So just like we pass command line arguments, those all those arguments we will put in this array, right? By convention, so there are certain rules that you have to follow. By convention, the first of these strings, that is argv0, should contain the file's name to be executed. So that is why we are not just passing the arguments. Strictly, the arguments for the copy program are the source path and the destination path, right? But as you can see, we are also passing the file name here in this argv. This argv is this full array, right? Another rule that we have to follow is that the argv array must be terminated by a null pointer. So that is why we have also included a null pointer. So there are four strings in this array. Two of them are the real arguments, that is the source path and the destination path. The first string is the name of the file. That is a convention that we have to follow. Also, the last element of this array is a null pointer. So here in this case, as you can see, args is an array of pointer to character arrays or strings in C, right? And the convention that we have to follow is that first element of this array should be the file name, followed by the actual arguments that will be passed to this program binary that we want to execute. So this foo.c and bar.c will be passed to CP, and you have to terminate this array by a null pointer. And as you can see, we are passing the first element of this, that is arg0, as the file name, and then we are passing the whole array as in place of this argv. So this is the piece of code, and then there is a printf statement, that is a printing statement after exec. So would this statement be printed or not? Think about this, and we'll answer this after we see the demo. So let's go to the terminal. This is the place where we will execute this code. So as you can see, exec1.c is the file name. We have understood this piece of code. So let me go ahead and execute this piece of code. But before I do that, so as you can see, we are currently in this directory 2.4.4. That is the name of this, the number of this video. As you can see, in this directory, there is one file called foo.c. We do not have a bar.c yet. This foo.c, I have put a string that says hey there. So just to be sure, let me print out the contents of this directory where this we will be executing this exec example. So as you can see, we have foo.c. Apart from them, all of them are other program files. But the point to understand here is that we do not have a bar.c, and that bar.c we will create using this code, that is exec1.c. When we execute this exec1.c, this foo will be copied and we will have a bar.c in this directory, that is 2.4.4. This is the directory, right? So let me execute this /exec1. So now what will happen is that this copy program will be executed. This exec1 program will be replaced by the copy program, and that copy program will make a copy of foo.c and create a bar.c. So if you pay attention here, we'll have a bar.c after I execute this. So no statements were printed, and now we have a bar.c which has the same contents as foo.c. Both of them have the contents hey there, right? So this bar.c was not there. So let me delete this for you once, and we'll execute this piece of code again, and you'll see bar.c appears here again. So what is happening here is that this exec1, when we are running this process, when we are launching this program, it is replaced by the copy program, and that copy program executes this, basically copies the foo.c in this directory and creates a bar.c, right? So this is how the exec works. And as you can see, no printf, basically this printf statement is not printed, because as we know, when the exec system call is successful, it does not return. So anything after this will not be executed, since this is a successful call to exec. So that is another important point, that when the exec call is successful, anything after the exec will not be executed. So that is why this printf is not executed. So this was example 1. So let's see one more example about the exec system call. So in this example, what we will do, instead of launching a Unix command, like basically in the previous example, we launched the CP command via the code. Now we will use our own program and launch it via exec. So here I have written a small simple piece of code that is called numbers. And all it does is that given a number, given an integer n, it will print from 1 till n, right? This is the for loop where we are doing the printing from 1 to n. So if you see, when we supply 10 to this piece of code, you can see 1 to 10 is being printed. So very simple piece of code. As you can see, we are when if you have to launch this program, then you have to give the name of the program and the argument. And these two are passed to this piece of code via the main function, right? So just like we know that anything that we write into the shell command line, the shell internally will call exec. So basically what I want to say is that we saw that when we type the copy command on the shell, internally something like this is done by the shell. So it will whatever we type on the command line, it will be converted into an array of pointer to character strings, and that will be passed to exec. So in the same way, when we basically type this command, that is numbers dot slash numbers and then 10, that will be passed to the main function like this. So internally the shell will convert this, will pass these two arguments in a array of character pointers, and then it will pass to the new program that we are launching via the main function. So the main function basically takes two arguments. One is argc, that is a count of arguments, and then this list itself. And from this list, the we can extract the integer n. So as you can see, at index 0 is the file name, at index 1 is the argument, basically the integer n up till which we want to print. So this 10 is present at index 1 in this argv array. So if we convert this into an integer, from that we can get the value of n. So this is how this piece of code that we have written extracts its command line argument, right? So when we launch this piece of code, it will extract the value of n which has been passed to it from the command line argument, and it will print from 1 up till that number n. So this is the piece of code, and what we will do, we will launch it in a programmatic way. We will write a piece of code and we will launch this using the exec system call instead of running it via the program, running it via the Unix shell. So again, we have to follow this convention that we have already seen. The first of this argv array should contain the file name. So we have given the file name dot slash numbers in the first element of this array, which is an array of pointers to char, right? And this array must be terminated by a null pointer. So this is the null pointer. So this is the list of arguments that we have. This array will be supplied to the exec vp system call, and the first element of this array contains the file name. Very similar program, very similar piece of code. Just in the previous case, what we did is that the command that we were passing was a standard Unix command. In this case, we are writing our own custom program that we want to launch using the exec call. So let's go to the terminal and see how it all works. So this is first of all, let's see the numbers. So this is the code for the numbers program, and I have already compiled this. So let me execute this numbers. Let's say I give 7. So as you can see, it prints 1 till 7. So this is how you launch this numbers program via the command line, right? So internally, the Unix shell would be passing these two arguments and like invoking the exec call, right? But now let's do that. Let's do the same thing in our piece of code. So exec2.c. This is the way we will invoke the numbers program via the exec system call. Here we did via the Unix shell. Now let's do this via our own piece of code. So exec2 will execute this one. So let me invoke exec2. So as you can see, what happened here is that we have supplied 10 as the argument. So this program printed 1 till 10, right? And this statement after exec was not executed. Why? Because this exec2 program, once it starts executing, it calls the exec call, and it never returns because it's successful. And on success, everything after the exec system call, it will not be executed. This printf will not be executed. So as you can see, we have invoked this numbers program programmatically via piece of code, and we have supplied 10. Let me change this. Let me make it, let's say 100. Now let me compile this piece of code again, and you will see the output will change. Gcc dot slash exec2.c minus o exec underscore 2. So let me again launch this piece of code. And as you can see, we have output up till 100. So this is how we can launch our own piece of program via the exec system call. So I hope these two examples give you an understanding of how the exec system call works. And finally, another point that I want to stress upon, that anything after the exec system call will not be executed if it is successful. Right. So this was the two examples where the exec system call is successful. Now let's see one final example where the exec system call fails. So now let us see this final example. So again, it's a very similar piece of code. All I have changed here is that I have replaced the call to the numbers program by a program which does not exist. I have just given a random name, number plate. I do not have this file in the directory that I'm going to be execute the file in. You can see, you can check. We have numbers.c, but we do not have any number plate, right? So this is a file which does not exist. And when we invoke the exec pp system call, so this system call will be, it will fail because it will not be able to locate this program file. So it will basically return. That is what I want to illustrate in this example, that this system call will fail. And so in the previous two examples, the file was there, the arguments were proper, so the exec system call did not fail. And there the execution, the statements after the exec call, they were not executed. Here what I want to show you is that when this system call fails, it could be due to any reason, and one of them is that the file does not exist. This it will return an integer, and that integer value we will be printing. So that's all in this program. So let's see what happens when we execute this piece of code. So this is the terminal, and let me first of all print out the contents of the directory. You can verify that we do not have the number plate program in this directory, right? So in this directory we do not have this, and when we will execute this exec3, right? In this exec3 we're trying to invoke the exec system call with number plate binary. So this will fail. So let me execute this exec3, and as you can see, it has failed. There were no, first of all, no numbers were printed, unlike when we called the numbers program. And the statement after the exec, it is also printed. So you can see exec returned, and the return value is -1. So this indicates that our exec system call has failed. And as you can see, the value of -1 has been returned in this case. So let's go back to our slides. So the point that I wanted to convey is that when the exec system call fails, this any statement after that will be executed, and the return value is -1. So this was it for this video. So in this video we talked about the exec system call. First of all, we discussed that why do we need an exec system call, because if you look at the fork system call, then all it does is that it creates a new process. It does not allow us to execute any new program. So that is why we need the exec system call. It allows us to launch new programs. Then we saw how it works, how it replaces the current process by a new program. Basically, it does not create any new process. It keeps executing the same process, but it replaces the current program with a different one. We talked about its return values, and we saw some examples of how the exec system call works. So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.